Right, so when we talk about parametric equations and defining a function parametrically, all that's saying is that for ordered pairs, we can put x and y in terms of a third variable, which we'll call t. So looking at this example, so I have my x and y in two parametric equations. This is the set of all ordered pairs x comma y. Okay. And x can be written as t plus 1, and y can be written as t squared plus t. And where t can be just any real number. Okay. So the first thing that I want to do is I want to find any ordered pairs that are determined when t is all these values from 3 to -3. Well, all I'm really doing here in this first step is I'm substituting t into both of these equations in the place where t is. So from here, what I'm going to do is I'm going to take each of these values of t. I'm going to start here with x. I'm going to take t and substitute it here. So let's see what happens. Okay. So -3, put in here. -3 plus 1, -2. -2 plus 1, -1. See, this is 0, and so on and so forth. 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. Okay, so those are my x values. Now for the y values, it involves a little bit more algebra because I got t squared plus 2 times t. So we'll start here. We'll start here, -3. So -3 squared, that's 9. 2 times -3 is -6. So 9 minus 6 is 3. For -2 squared is 4. Because remember, if you're doing this on paper, please remember that this right here is not the same as this. Okay. Because this right here, if you remember order of operations, you take parentheses and the exponents first, right? Here, I just have an exponent. So the exponent only applies to the 2. It doesn't apply to the negative side. That's why this is -4. However, if I put parentheses around the -2, then that's just -2 times itself, which is +4. Okay, so please remember that. All right. So, anyways, back to where I was. -2 in here. -2 squared is 4. 2 times -2 is -4. So 4 minus 4 is 0. Okay. Then I got -1. So -1 squared is +1. 2 times -1 is -1. So no, I'm sorry, -2. 2 times -1 is -2. So 1 minus 2, that's -1. So for 0, that's just going to be 0. For 1, so that's 1. This is 2. 1 plus 2 is 3. For 2, 2 squared is 4. 2 times 2 is 4. 4 plus 4 is 8. If I do 3 right here, 3 squared is 9. 2 times 3 is 6. 9 plus 6 is 15. Oop, not 16. 15. 15. Okay. So now I can put these together as an ordered pair, x comma y. So -2 comma 3, -1 comma 0, 0 comma -1, 1 comma 0, 2 comma 3, 3 comma 8, and then 4 comma 15. All right. So there are x and y values. So that's the first part. Next part that I want to do is I want to find an algebraic relationship between x and y. Oftentimes that's called eliminating the parameter. Okay, and we got to ask ourselves: is y a function of x? Okay, so first off, if I want to find an algebraic relationship between x and y, I need to see that y is x and y can fit together. It's kind of like solving a system of equations, right? So, let me find the next step here. Yes. So, for example, here, if I have x equals t plus 1, if I subtract 1 on both sides, here's what I get. I get t equals x minus 1. Well, if t is x minus 1, let's see about substituting that into y to get y as an equation of x. Okay? So let's do that. So let's take this value for t and substitute it in here. Okay? So that's, let's see, make sure you can see. Yeah. So that's y equals t squared, so x minus 1 squared, plus 2 times x minus 1. Okay? So, and of course, don't forget, x minus 1 times itself, we got a FOIL. All right? And then so we're going to FOIL first, outside, inside, last, and then distribute. We're also going to distribute the 2 also. Okay? So first, x times x is x squared minus x, and then negative 1 times itself is plus 1. And then I have plus 2x minus 2. All right? So now I'm going to go ahead and combine some like terms here. So x squared, so here's some like terms and here's some like terms. So negative 1 minus 1 is negative 2. Negative 2x plus 2x is 0, so those actually cancel each other out. And then I'm just left with 1 minus 2, which is negative 1. So y as a function of x is x squared minus 1. But is it really? If I take these ordered pairs, and I plug in their x values, do I get the y values? Well, let's find out. So let's try negative 2. So negative 2 squared minus 1, that's negative 2 squared is 4, 4 minus 1 is 3. Okay, so far so good. Let's try this one. Negative 1 and 0. So that's, I'll do it here. Negative 1 squared minus 1. So negative 1 squared is 1. 1 minus 1 is 0. So that all checks out. You can test all these other points too. But we're going to find that this graph is indeed a function. Y is a function of x. And of course, if you want to graph it, just take the x and y values and put them on a coordinate plane. So, like for example, if I were to do that over here, okay, let's see. Let's see. Negative 3, negative 2, negative 1, 0, 1, 2, 3. Then let's see. 1, 2, 3, 4, 5. 2, 3, 4, 5, 6, 8. 1, 6, 7, and then a little bit more 8. All right, I'll just go ahead and plot some of these. So negative 2, 3, that's down here. No, negative 2, 3 is up here. Sorry, I was about to put it in the wrong place. Negative 1, 0. 0, negative 1. Positive 1, 0. 2, 3. Oh, wrong place. There we go. 2, 3. 1, 2, 3. And then so on and so forth. So what's going to happen here, I have this neat-looking parabola right here. And looking at this parabola, it passes the vertical line test. So that tells me that this is a function. These values are going to keep going out this way. These values are going to keep going out that way. That relation represents a function. Okay? Now, where we get in trouble here is when it comes to inverses. Okay? So, an inverse of a relation, so let's say I have a relation of with an ordered pair of a comma b. So that's in the relation right here. If I want the inverse of that, all I have to do is just switch the variables around. So if a comma b is in my original relation, then b comma a is in the inverse of that relation. Okay? Let's use this as an example. So here I have y equals t squared plus 2t, and x is equal to t plus 1, aka t is equal to x minus 1. Okay? Now, let's say, I'm going to use this side of the board again. Let's say I wanted to find the inverse of this relation. All I have to do is switch these around. So this now becomes the x, and this now becomes the y. So let's see that in action here. So this is my original relation with the parameter. Okay. So now this time x will be equal to t squared plus t, 2t, and y will be equal to t plus 1. Okay? This time y is now equal to t plus 1. So when I go to graph this relation, so that tells me if I plug in the same values of t, the question remains, will all these still fit, but just in the opposite places? Let's find out. Okay. Well, turns out it actually does. If I look at t, right, for my y values, I'm gonna do that one because that's the easier one to look at. So because all I'm doing is adding 1 to each one of these. -2, -1, 0, 1, 2, 3, 4. And then for -3, again, same equation, right? T squared plus 2t. That's -3 squared plus 2 times -3. That's 9 minus 6, which is 3. And then I'm gonna end up getting the same things because I didn't change the equations in any way. 3, 8, and 15. Okay. And as it turns out, I still want to write this as an equation of x, but here's the problem. Here I have t plus 1 right here. Okay? That means that t is equal to y minus 1. Well, if I plug that into here, I no longer have y as a function of x. Instead, I just have x as a function of y. Okay? So, go ahead and look further into this here. All right. Okay. But that doesn't mean that we can't, doesn't mean that we still can't find the inverse of that. But the way that this works is a way that we can connect this to actual functions is, so here's my function, y equals x squared minus 1. Okay. Now, if I try to graph this, so 3, -2, -1. No, sorry. If I try to graph these points here, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 2, 3, 4, 5. So let's try to graph these points here. So 3, -2, that's down here. 0, -1 is up here. Yeah. Then -1, 0 is up here. Oh, sorry, this is in the wrong place. 3, -2, right here. Then 0, -1, or -1, 0. Then 0, 1. And 3, 2. 1, 2, 3, 2. And so on and so forth. And then A3 is all the way up here. What's going to happen here is I end up with this graph right here. Now the problem with that is this graph doesn't it doesn't pass the vertical line test, and because it doesn't pass the vertical line test for this, our inverse relation cannot be a function. But it can be if we only restrict ourselves to, let's say, if I restrict the x values for my original function to these 4 or these 3. Okay. Then what's going to happen now is I have this graph right here, and that does pass the horizontal line test. Sorry, I just gave it away. It passes the vertical line test here. Now the way to check before you even start doing anything, in order to check that the inverse relation can be a function, is what's called the horizontal line test. Now, the horizontal line test is very similar to the vertical line test. So when you use the vertical line test on a function, you test to make sure that no x value has more than one y value. So here, if I draw a vertical line here, notice that no one x value crosses that line more than once. When it comes to the horizontal line test, since we switch the x and the y, then what's going to happen is that horizontal line test that we test with the x values now gets turned on its side to test the y values. Okay, so to make sure that no one y value has more than two x values in it. Okay, and anytime that happens, this is what's called one-to-one. A function is one-to-one if every x value has one unique y value. See here, this doesn't cut the mustard here. If I restrict the domain to only positive numbers, starting here, then I end up with something like this that not only passes the vertical line test, but also passes the horizontal line test. Okay. Now to go over how do we get the inverse of a function using this information? Well, when we found the inverse relation, when we switched these two around, so the y's in here now became the x's, and the x's now became the y's. So in a way, that's kind of a template for us to get started. If my function is this, let's say this is f of x, and I want to find its inverse. Well, the first thing that I want to do is make sure I write it as y equals x squared minus 1. Now, why do I want to do that? I want to do that because just as we switch the x and y here to get the inverse relation, we're going to go ahead and switch the x and y here. So that now, x is now equal to y squared minus 1. Okay. And if you think about it, it kind of makes a little sense, right? If this is my relation here, and I try to write x as a function of y for this. So if I try to take this and put it in here, let's see, that's t plus 1 squared. I'm sorry, that should be, no, sorry, messing up. Because of this right here, t is now equal to y minus 1, okay? So if I try to take that and substitute it here, then that's y minus 1 squared plus 2 times y minus 1, okay? If I FOIL this out, y squared minus 2y plus 1 plus 2y minus 2. Again, these cancel. 1 minus 2 is negative 1. Y squared equals negative 1. Or y squared minus 1. I'm sorry. X equals y squared minus 1. But again, now that we switched x and y, I want to go ahead and write y as a function of x, because we get a brand new function, and we get a brand new function when we switch relations. Okay, so again, when you're solving equation, when you're solving to find the inverse of a function, first thing you want to do is change f of x to y. Now, f of x and y are the same thing; they're interchangeable. And the reason why you want to do this is because just like we switched the x and y from here to here, we're going to switch the x and y from here to here. Okay? And then from there, it's just solving for y. So that means adding 1 on both sides. That gives me y squared equals x plus 1. And then I have one more step. Take the square root on both sides. So y is the square root of x plus 1, which is our inverse function. Square root of x plus 1. So again, why do we switch the x and the y? Well, with our parameter here, when we switch the x and y from one relation to the other, that means that we're switching these parameters right here. And when we switch these parameters, and I write one as a function of the other, this is what I end up with. But if I want to write that as a function of x, y is a function of x, I need to solve for y. Okay? And that's the relationship between, that's part of the relationship between inverses and their functions. Now there's one part, functions and their inverses, when it comes to parameters. There's one other thing that I want to show you, and that has to do with function composition. Now, if you remember function composition, or if you've ever done it, I have one function f of x and one function g of x. Okay? I can compose one function inside of another. Like I can take g of x and substitute it inside of f of x. Okay? So let's say this is my f of x. Let's say this is my g of x. Okay? Let's say I want to take f of g of x. I want to take this function and substitute it inside this function for x. So let's see what we get. Y equals. Since I'm substituting this, I got to put it in parentheses. Square root of x plus 1 squared minus 1. Okay? And then just, simplify. This square root and this exponent will cancel each other out. That leaves me with x plus 1 minus 1. Those cancel out. And I'm just left with x. What happens if I go the other way around? I'm going to do it on this side. What happens if I, instead of plugging g into f, what if I wanted to plug f into g? That's called g of f. So that's g of f of x. So this time I'm going to take this function and plug it into this x right here. So let's see what happens. That's g of x squared minus 1. So I'm going to take x squared minus 1 and substitute it in here. Square root of x squared minus 1 plus 1. So let's simplify. Got to take care of that addition first. Negative 1 and positive 1 cancel each other out. Square root of x squared. So now I just have x squared by itself. Because this is a perfect square, it cancels out that square root. And I have x again. So that's another relationship between a function and its inverse. If I compose one into the other, both ways, I get x both times. Okay? And again, graphically, this is called being one-to-one. If a function's one-to-one, then its inverse will also be a function. Every relation has an inverse. Every function will at least have an inverse relation. But the problem is that relation also going to be a function? That's why the horizontal line test is so important, because it helps to tell us, hey, I actually have an inverse function that I can find, and that works. Okay. I hope this helps. Just let me know if you have any more questions.